Okay, so this is the Ladi Chaos tutorial for version 2. Start the GUI. Next step is to import the dataset. It's done up here. You can define, as in the previous version, a boxcar averaging range. Next is to load the DM. Pick this one that's already in the same folder. Wait until it's imported. And then plot the overview plot. This is a hillshade. It's always using the hillshade options provided in here. Goal in this overview is to identify the displaced feature, and in this case I want to focus on this part here. So next step is to define a zoom box that is a subset of the overall data set. Doing so improves the speed of this measuring approach by quite a bit. So now we have our zoom box, and we can plot the data sets. Here we go. You can play with the options here. So for example, I don't want to use hillshade but slope. Here's a different plot. Then I can also invert the color maps, such as this, or also change the maximum minimum value that is used. Very important is to use the contour option. You know, so the contour is now included. Yep. So here's one of the features, one part of the feature, and the other one is here. If you don't want the contours anymore, just put some non-number value, enter it, and then you can see it's not used anymore, and the plot is refreshed in such a manner. So, but I want to use contours. Here we go. Next, zoom in quite a bit and make this a big plot. Something I haven't mentioned yet, but it's important. It's one of the main features of this tool actually is the ability to do this blind measurement. And so I want to click this. So here's my zoom. So next step is now to trace the fault. Oops, that was wrong. Just redo it. So you can then, if you don't like your trace, you can either retrace or just shift or rotate the feature, this main trace, in these these options here. For now I'm happy with this choice. So next thing is I have to define the position of the two fault parallel profiles, the red one and the blue one. So first the red one, take it 10 meters away, it's right here, okay, and do the same thing for the blue one. And I want to zoom in even more. Okay, so I'm sufficiently happy with this. You can also look at the swath width. It's basically, you can see now is a box, and it's the box. The dataset within that box is what's used for the profiles that you can see here. So now you see the red and the blue lines. Next step is to actually crop the red profile to the extent of the feature that you want to fit. Let's make it this size and then replot. So you can see here is the channel itself. You can zoom in a bit. You can see it better now. That's the feature. And basically this one, I think we want to match with this guy here. As a next step, we come to this box 4 and trace the different features. So always just a left click with the mouse, and if you don't like a point, just right click and go over the fault, over the profile, and once you come to the fault itself, you can define the position. You project in, so then you press F. You can see there's not a circle now, but a square and space, and this feature is done. If you don't like it, just press this button again. We do the same now for blue. And also now project into the fault by pressing F. And yes, that's good enough. Okay. So now we have done these things. Next step is to plot these longitudinal profiles. This step always takes a bit long, I have to admit. Okay, here are the longitudinal profiles. You can also see the position of the fault trace and our two fault parallel profiles. So next step, we are done with 4. We now go to number 5. First, the projection point. This is usually the position of the fault itself. And then we trace both features. First the red, and then also the other one, the blue. So this was the traced. Here you have then the traced values for vertical and horizontal displacements, just from the line drawings you've done. The next thing is to calculate the best offset, and I'm gonna just anti-maximum minimize around this value that is provided up there. So horizontal is going to be between 10 and 30 meters, and vertical is going to be between 0 and 2 meters. This is some stretch factors. Okay, so let's find the offset. So here's the original position from both profiles, from the red and the blue, and now here's the shifted one. You can zoom in if you want to check if it's a good fit. It seems to be not the greatest fit. I think it has to move over a bit more maybe, but for now I'll just leave it as it is, because it's only for demonstration. Otherwise, what I would do probably is cut off this part here. So in that case, we have to crop the red profile again to a different value. See if this works better then. Okay, that's not what I wanted. And then come back here to find the best offset. Nothing happened because I didn't redraw this profile. So now it should be better. So if I press this button again, I can see profile fits better, and the shift amount of slip changed as well. So you can see it's now by 21 meters and 1.1. So these values you could, for example, then use to check if this is actually a good approximation with the backslipping approach. This is the backslip of the longitudinal profiles. So for example, if you now draw a line here, you can figure out if this is reasonable or not. It's very crude doing it this way, of course, but you just get the point, I guess. So here is the backslip, and it looks strange in a way because the slope is now not inverted anymore. So let's do this again. That was just because I accidentally pressed this button. So then you can look and see, yes, this is a good fit, and enter it, for example, then here as your optimum value. You can then also have to assign a rating for horizontal and vertical displacement, and also define maximum min. I just enter some values now for the sake of this tutorial and to save some time. Same with the displacement. So put some values here. So now we're almost able to save and finish this measurement. You can here define UTM zones. This is good because the GUI itself generates a KMZ file, and this puts it in reference. You can then use a distance to a reference point, distance along fault. Let's put some random value here and some comment on the feature that you have measured, and whether you have any other further description about the offset. So basically what you have is 3 measurements. You have one from the tracing, you have one from the optimal displacement that you've defined via this calculation step, and you have one from backslipping. They don't have to be the same, of course. So the last step now is to save, and that's done here, this save button, number 9. save name, and this will automatically generate a number of plots and the website too. It takes a few moments. So saving is now completed, and we're done in a sense.